Hello, everyone, and welcome to today's live broadcast, sCMOS Observations at SwissOGS, presented by Dr. Emiliano Cordelli and Dr. Ines Juvan-Beaulieu. I'm Christy Jewell of Labroots, and I will be your moderator for today's event. Today's educational web seminar is brought to you by Labroots and sponsored by Andor. For more information on our sponsor, please visit andor.com. Now let's get started. I want to remind everyone that today's event is interactive, and we encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. We will answer as many questions as we have time for at the end of the presentation. If you have any trouble seeing or hearing the presentation, just use that Ask a Question box to let us know you're experiencing a problem. Today's webinar is educational and thus offers continuing education credits. Just click on that Continuing Education Credits tab at the top of your screen and follow the process to obtain your credits. I would now like to introduce our first speaker, Dr. Emiliano Cordelli. Dr. Cordelli is a researcher at the Astronomical Institute of the University of Bern and currently in charge of research and development at the Swiss Optical Ground Station and Geodynamics Observatory, Zimmerwald, SwissOGS. His areas of expertise include orbital and attitude dynamics of artificial objects, covering also the orbit and attitude determination of space debris. He has observational and analysis experience of satellite laser ranging, astrometric, and photometric measurements. For a complete biography on Emiliano, please visit the Biography tab at the top of your screen. Emiliano, you may now begin your presentation.
Thanks, Christy. Hello, everybody. Today I would like to talk to you about some CMOS observation that we perform here at the Swiss Optical Ground Station Geodynamics Observatory, Zimmerwald. So just a small presentation first. The Swiss Optical Ground Station Geodynamics Observatory in Zimmerwald belongs to the Astronomical Institute of the University of Bern. Here we perform research activity focusing on the space debris, on the space surveillance, astrodynamics, satellite geodesy, and global geodynamics. In order to support these research activities, the SwissOGS is performing 24/7 based operation, and what we are our telescope during the night observe especially space debris, asteroids, comets, supernovae. While during daytime and nighttime, we have a satellite laser ranging system and a GPS receiver or GNSS receiver working 24 hours per day. We, of course, being part of the university, we have also some teaching module in astronomy. So a short outline of this talk. I will briefly talk at the beginning about the hardware that we are using, where the camera, the CMOS camera is integrated, and which software we needed to develop in order to do some particular observation, and then I will talk about the kind of observation that we are performing. So we do some lucky images, some observation about asteroids. The camera is also used as a tracking camera in parallel to the satellite laser ranging activities. Then we were able recently to extend our camera observation also to daytime operation, and finally what we can get in terms of space debris and how this measurement can be useful for orbit and attitude determination. Okay, starting from the hardware. So all the observations that we will see later on are acquired with the Zimmerwald Laser and Astrometry telescope. This is 1 meter class telescope. It's pretty versatile. We have different experiments ongoing on this telescope. We have, as an example, one CUDE path for the satellite laser ranging system. Then we have, in the NASMIT platform, we have 4 focal stations with different focal lengths. In one, there is a CCD camera. In one, there is a photon counter detector that is just for experimental use, and is under testing at the moment. And then today we will talk about mainly the operation that we perform on the CMOS camera. Since the CMOS camera is running in parallel to the laser observation, we needed to add the filter to block the laser light, to prevent the laser light reaches the sensor, because we don't want to damage the camera. And then since we extended also the observation during daytime, we added also a sky filter to cut out the light of the sky, as we will see later. So once again, this is our telescope, some particular in front, from the back, and we have the NASMIT platform. Why the NASMIT platform is interesting for us? Because as we can see here, there is the camera installed, and just the particular here you see how the camera fit, and on the right of the picture you have the focal reducer. We have the focal reducer. For more details about this camera, I would leave the link to go to the Andor website. What is interesting, of just small information, the 22mm diagonal field of view of the camera allow on the focal length that we're using, the 8-meter focal length, a field of view of 6 by 7 arcminutes. It is important for the application that we are going to see now. So starting with the application, we know, being a research institute, part of the university, we are also performing some educational observations. So in the right side of the slide, we see the results of a series of images acquired for the moon. It's very nice to see, for students at least, it's very nice to see the details on the surface of the moon, like craters, and actually it's easy from the picture measure the dimension of the craters, and with some math more we can measure also the height of the mountains and of the crater, knowing the position of the sun and the position and the amount of the shadow that we see. Then some funny tests where we performed some funny tests with the lucky imaging. Actually, we assume that the atmosphere is made by air lenses, and if you are lucky enough, one of these lenses will be on top of your telescope and will compensate the effect of your seeing, delivering so very sharp images. So this is the problem, is that for 1 meter telescope to have 1 meter air lens is a bit more rare. So you don't have a perfectly sharp image, but nevertheless here is interesting to see on the left picture an image of the International Space Station, from which one can distinguish quite easily the body of the space station and the solar panels. Okay, let's move for more, let's say, scientific results. So this is an example of the picture taken with the CMOS camera when it was in the 4 meter focal length. The effective field of view, in fact, is 12 by 14 arcminutes. We performed an observation campaign of the asteroid 2012 TC4 during its flyby around the Earth. Actually, this satellite, this picture was observed the night of the 11th of October, and the satellite was, this asteroid was passing at a distance of 44,000 kilometers from the Earth. In terms of astronomical distances, this is pretty close actually, and it was just 8,000 kilometers above the geostationary ring. That is one of the most crowded space regions that we use for human activities like television and remote sensing, meteor observation. So what we can see in the center of the image, we see the asteroid, and then we have also the limit, let's say we highlighted also one of the faintest stars that we could get with using this camera and only 2 seconds of exposure. So, but okay, this is just a picture. Now I will show you a video about these asteroids. From the analysis of this video, this was not the only video that we acquired that night. Actually, it's not really a video. We acquired 7 series of images, each one containing roughly 200 images spread over 2 hours and 20 minutes. If we analyze the brightness variation of the light reflected by the asteroid over this image series, we get this segmented light curve. Nevertheless, this segmented light curve allowed us to perform a phase reconstruction procedure that allowed to extract the phase diagram of the object that we can see on the right. And this, once we are able to get a sharp phase diagram, we are also able to extract the rotation period of this asteroid. This is very interesting because knowing the phase diagram, all the astronomers were inferring the shape of the asteroid, while we could extract also this rotation period that was confirmed also by the results found in the literature. More extensive work on this CMOS camera was performed because we wanted to use the camera to support the satellite laser ranging observation. Actually, when performing a satellite laser ranging, we know already where the object that we want to track is. This is usually our geodetic satellite whose orbit are really precise. But nevertheless, some ephemeris are not accurate or not very accurate, or at least not always. So the idea was to use, to employ this camera to have a stream video, and knowing the position of the object, of the laser beam, into the camera, and seeing the position of the object, we could correct the pointing offset of our telescope, facilitating the target acquisition from the SLR system. So we needed to develop a software that is able to communicate with the laser software, send them correction, and at the same time is able to communicate and adjust camera parameters like the exposure time, the shutter mode, the readout frequency. If you want some binning, we also implement some capability to store the images, and we will see just later why this is important. So I show you a screenshot of the software in operation, and here we have an example of the target satellite was TOPEX. As later, I will talk quite often about space debris objects. So TOPEX in this case, and as an example of a space debris, is a defunct satellite, is not operational anymore, and of course the ephemeris are not accurate anymore. Actually, what we see here, we see on the red cross in the image, we see the position of the laser, and we see also the position of the object as given by the ephemeris. In particular, the red cross is where the ephemeris are telling us to point, while the white dot is, you see, is an offset. Then we were able, by clicking on the object, to correct and align the object with the laser. And as you can see in the small black window, we see some yellow dots. These yellow dots indicate that the laser pulse was successfully detected from the laser system. And on the background, I also show the image stored for this object. So why this is what is nice about this software? What we are it's very important for us because this software with one single observation session allow us to get observation that can be used both for the attitude and the orbit determination of the object. And this is very important for space debris observation, not too much for improving the laser performances, as we will see later, but for space debris observation is fundamental. The merging, the data fusion, especially when observing from one single station. So, quickly, we see these are a summary. This slide contains a summary of the observation collected by the tracking camera. We have the position of the object in the sky, given by directly by the angular encoder of the telescope. And this is also an advantage because the small field of view of the camera and the short exposure time, especially for LEO satellite, will not allow us to have enough star that can be used for classical astrometric data reduction procedures. So we have the angular measurement, and then on the top left we see the difference between the measured distance and the one provided by calculated by the ephemeris. At this point, if from this distance we remove the contribution of the orbital motion, we have in the middle graph we are able to highlight the contribution to the measured distance given by the attitude motion. Actually, the laser measurements are very precise, let's say around the centimeter accuracy. And then we are able to range to MVSAT in this case because one of its payload is a retroreflector array. This retroreflector array is not in the center of mass of the object, and since the object is rotating, we are able also to evaluate the rotation of the center of the retroreflector around the center of mass. Finally, in the last graph on the bottom one, we see the results of the analysis of the images. Analyzing the brightness of each frame, we are able to extract a light curve. Very interesting for the space debris observation, and especially for attitude debris removal operation in future will be the proper attitude determination of the object. So not only the rotation period, but also the direction of the rotation axis of the object, because in future, once we want to go and grab the object, we should know how to approach it. And both these information can be retrieved by there are studies on how to retrieve this information from the data merging ranges and light curve. Then, before moving to other applications, I want to show you how the performances of our laser software, the performances of the laser acquisition were improved by the employ of the tracking camera. Over the same amount of time, we are able to shorten the acquisition, to shorten the time needed by the system to lock on the object. That means we are able to observe more objects in the same amount of time, to get more observation, and each observation has a higher accuracy because we don't deliver single observation, each row observation, we deliver what is called the normal point. The normal point is calculated by averaging the single observation. Of course, the average is more accurate the more the number of measurements involved. Then we decided to, by accident, doing some tests, I was able to see a satellite during daytime. So I decided to do first some math, and then to verify that we could see satellites during daytime, and then we did some first tests at noon as an example, where I pointed the telescopes to different stars with different magnitude, from the brightest on the left to the faintest on the right, and that confirmed the math that I did, and we are able to see up to magnitude 7 during full daytime. Actually, these pictures were acquired at noon. Something that make the daytime observation a bit more difficult are the strong gradient, brightness gradients in the sky. Toward the horizon, the sky is brighter than at the zenith, and of course, the brightness of the sky depends a lot also by the distance from the sun and from the weather condition. A dry day is better than a humid day. Then, okay, we verified that we are able to do something during daytime, so I decided to do some tests over satellites. Here we have just a GIF that I created using 25 images acquired for this satellite. This is a standard satellite laser ranging target, and this was observed with 0.1 seconds of exposure around the sunset. What is interesting from these images is that if we look at the object, we see that the object is not always point-like, but is changing. These are the effect of the seeing, atmospheric seeing, and in principle one could do also some research about the speckles that we see. Then interesting is how the sky background is, the brightness is increasing very fast, over 1.5 minutes of time interval between the first and the last image. The sky background, the sky during daytime acts as an homogeneous source of light, and this homogeneous source of light at the end was showing us some dark spot on the camera. This is not due to the camera at all, but this is simply dust on the focal reducer. So to improve the quality of the image, especially the one acquired during daytime, what we can do is a flat fielding of the image. This allows us to remove some vignetting and also the effect of the dust. And this improves the detectability of the object. At the same time, also to improve the performances during daytime, we decided to analyze the sky spectrum, taking into account the transmittancy of the focal reducer and the camera quantum efficiency. So we have everything is summarized in the plot over here, and this is the radiance of the sky all over the visual spectrum. So in order to improve the performance during daytime, we decided to insert a long passage filters with the cutting edge at 500 nanometers to cut out some of the blue light of the sky, and this allowed us to increase the signal to noise ratio on the same source reduce the sky background flux by something about 40%, and this translates directly into an increase of the exposure time that can be used to detect smaller objects in the sky. So now let me talk about why daytime observation, why the use of the tracking camera and the use of different kind of observables is important for the orbit determination, especially if we talk about space debris. So what we performed some tests. We acquired observation during 1 and 2 passes during daytime and 1 and 2 passes during nighttime, and then we compared what we can get in terms of accuracy, processing separately 1, 2 passages, processing separately the daytime observation with respect to the nighttime observation, then putting them together. And then we played also on the kind of observables that we are collecting using the tracking camera. The first analysis was done on AGSI. AGSI is a standard tracker for the laser community, and this allowed us also to have some reference orbit against which I could compare my orbit determination result. And essentially what we can see is that the effect of the merging of the data fusion can be seen especially for the one-pass case. For the nighttime one-pass case, if we use only angular observation, we will have an error over 4 days, an average error of 100 kilometers, while if we use merged data, the error reduces to 130 meters. Then, if we now, instead of using only nighttime observation, during classical space debris observation, you can rely only on nighttime observation, since the satellite has to be illuminated, the object has to be illuminated, but the observer has to be into the shadow, because actually this is the limit of the technology. This is a limit of the CCD cameras, that they cannot go for very, very short exposure time due to, for us as an example, is a problem. The problem is caused by the external mechanical shutter. This is solved by the CMOS that use an electronic shutter. Then one last comparison that I want to show you is the improvement given by the merging daytime and nighttime observation. And this is visible from the small plot on the top, where we can see that the green and red segment is the portion of arc that usually we can observe if we rely only on nighttime observation. Extending the observation to the daytime, we are able to observe almost a quarter of an orbit. And this is translated directly into the orbit determination accuracy. If comparing one passage during nighttime, we have an accuracy again of 100 km that reduce to 100 meter, even processing only angular observation, if we put together daytime and nighttime passes. The best solution that we got was 27 meters of average error over 4 days of propagation, and this is quite important for space debris activity, since before this kind of observation we didn't have any a priori information about the orbit, so we could really perform what is called an initial orbit determination and then a successive orbit improvement that allowed us to reduce the covariance and the uncertainty region of the object position to a radius of, let's say, 20-30 meters. This is important for collision avoidance maneuver. The space is crowded of space junk that are very dangerous for the satellite, since each and every particle have an high energy that could potentially destroy our mission. Knowing precisely where these objects are reduce the non-necessary maneuvers and enlarges the lifetime of the satellite. Okay, but you're telling me, yes, you used the satellite that we know already which is its orbit. So we decided to perform some tests also to space debris. This is TOPEX. Since I didn't have any reference orbit for this object, I needed to observe it in 2 consecutive passes. I used the measurement collected during the one pass to determine an orbit that was propagated and compared with the observation collected during the second pass of the satellite, always using our tracking camera. So here what is interesting to see is on the left plot we see the rapidity of the attitude motion. And as we will see later, this object will rotate with the rotation period of 10 seconds and is still spinning up. And this speed is also increasing. And then what is interesting to see is that using merge measurement, we can improve our orbit determination accuracy by 1 order of magnitude if we look only at the angular position, by 2 order of magnitude if we look at the estimation of the distance between the observer and the object. But these are low Earth satellites. We could also prove that we were able to range also to high altitude satellite. This is the results. These observations were collected to a debris that was former GLONASS satellite. This satellite is orbiting at around 20,000 kilometers. And the improvement using merged with respect to homogeneous measurement is less evident, but because the distance between the 2 series of observation is smaller in time, and these 2 series of observation belongs to the same path of the satellite. What is interesting from the left plot is the position of the good echoes, the yellow point of the laser, with respect to the light curve that we are observing. Actually, the light curve shows some pattern, but from the pattern itself we are not able to determine which part of the satellite we are currently observing. And this information is provided by the laser. We know that the retroreflector for this satellite is in the nadir phase of the satellite, means that the yellow region, the portion of the light curve that corresponds to the yellow region of good echoes, this is exactly the nadir phase of the satellite. Why it is digression? Because this led me the connection to the measurement that can support the attitude determination. Actually, knowing which is the nadir phase of the satellite, we are able to perform what is called a 3-axis orbit determination. Why the orbit determination is 3-axis attitude determination? Why the attitude determination is important? Again, is important for mainly for active debris removal mission, where we have to know from which direction is better to approach the satellite to grab it, to the space debris, to grab it and pull it down. Or if we can do also some environmental studies. Here in this slide I showed you the light curve acquired, the high resolution light curve acquired with the CMOS camera using half of a second of exposure we were able to discriminate some specular reflection given by the peaks that we see in the light curve of this rocket body. This is a rocket body can be assumed as a cylindrical shaped object. So if we analyze the assuming that this object is in a flat spin condition, the rotation should produce a brightness variation that looks like a sinusoid. And this is exactly what we see here if we exclude the maxima of the peaks given by the specular reflection and these relative minima that probably is caused by one of the sides of the rocket body. It's difficult from the light curve itself to discriminate which is the nozzle and which is the adapter side of the payload. But what is important is that from this measurement we can extract the rotation period as for the asteroid, and in principle, knowing also the shape of the object, one can infer also the direction of the rotation axis. These two data could be used to do also some environmental studies of to evaluate what are the torques that are acting on a spacecraft. Again, I took over the same example as before, topics, and later we will see a GLONASS to show you how the details that the CMOS camera allowed us to extract from the light curve and the influence of the change of the observation geometry. When analyzing light curve, the position of the sun, the relative position of the object with respect to the sun and the observer is important, because in relation with the attitude motion, the light reflected toward the observer is different. This is exactly what we see here on the bottom plot. This is the same satellite acquired in a time distance of 2 days. The rotation period is pretty similar, but in the first case we see relatively flat behavior over the path. We have only in a portion of the path some specular reflection, while on the second pass we have an increase of the brightness due to probably the reduction of the phase angle. And even if the target satellite is the same, the features shown in the two plots are quite different. The same is valid for the higher altitude satellite. We used an exposure time of 0.7 seconds this time. And again, this is the same GLONASS as before, so the two series of observation were acquired with a distance in time of 20 minutes, roughly. And we can see that the effect of the change in the observation geometry. There is, on the second part, on the right plot, we see a higher difference, a bigger difference between the absolute maximum and the relative maxima of the light curve. But what is interesting now, what we can do during daytime, the observation geometry and the illumination condition change pretty fast during daytime. And then here I will report some results acquired really during daytime. On the left side of the slide, we see the results obtained for Envisat during daytime and during the sunset. During daytime, we didn't yet use the sky filter, so the light curve is pretty noisy. Nevertheless, we have some feature that can be identified also into the second plot. A second example on the right side is obtained for a rocket stage. Again, this is a cylindrical object that should rotate around its maximum axis of inertia. This is an assumption that we can do since in the space there are some dissipative torques that let the object migrate from the spin around the minimum axis of inertia toward the maximum axis of inertia. What is interesting here is the change of the observation condition in relation to the attitude motion. We see at the beginning the light curve is pretty flat, but then toward the end some features start to appear and start to be amplified. And this is exactly the contribution in the reflection given by the attitude. So that brings me to the summary. So the CMOS camera were used for a huge variety of applications, from the lighting images to the observation of asteroids. We used the tracking camera for support of the, we used the CMOS camera as tracking camera as support of SLR observation. This allowed us to get observation simultaneously for the orbit and the attitude determination. This is important because this kind of camera could allow us to track objects that are either yearly launched or which are re-entering in the atmosphere, where the ephemeris are of poor accuracy. The camera allowed us to observe light curve with an extremely high resolution that usually is not possible with CCD camera. And finally, we were able to extend our observation time also during daytime. And this is in the table. I just put a summary of all the objects that varies from satellite to rocket stage at different altitude that we are able to observe only during daytime. So that's everything from my side, and thanks you for your attention, and thank you, Christy, for the opportunity.
Thank you, Emiliano, for that informative presentation. Now, kicking off the second part of our webinar today is Dr. Ines Juvan-Beaulieu. Dr. Juvan-Beaulieu is an astronomy specialist at Andor. She studied physics with a primary focus on astrophysics at the University of Graz in Austria. In April 2018, she completed her PhD thesis in multicolor photometry of transiting extrasolar planets. In addition, she has held a research position at the Space Research Institute in Graz and spent some time lecturing at the University of Innsbruck. For a complete biography on Dr. Juvan-Beaulieu, please visit the Biography tab at the top of your screen. Ines, you may now begin your presentation.
So thank you, Christy, for the introduction, and thank you, Emiliano, for talking about the observations that you perform at the Zimmerwald Observatory. So my part is now to talk about Andor's camera solutions for large sky surveys and near-Earth object studies. So at first, I would like to talk about Andor's camera solutions for astronomy in general. So we have a variety of options. We offer large area and high resolution CCDs. Then we also have sCMOS and EMCCD camera solutions, especially for high time resolution astronomy, or if you have to deal with low light conditions. So in that case, EMCCD cameras would be the perfect solution for you. And also, I would like to highlight that we do offer camera customization. And just so you have an overview of in which projects Andor is involved in, so which projects use cameras, we have, for example, our EMCCD cameras called the Ixons, used at the Sophia telescope. So they're used for as guide and science cameras. Then also Andor cameras are used for exoplanet transit observations, like for example the NGPS survey. There they use several Icon Ls, which are also customized. So those are 2K by 2K CCD cameras. Then we have two SILA cameras. Those are sCMOS front illuminated cameras used for the Neviota survey. So that means near-Earth object lunar impacts and optical transient studies. And then we also have several Ixon EMCCDs used for adaptive optics projects, like the Naomi project at the VLTI. But now I would like to come back to large sky surveys. So if you perform such surveys, I would recommend to use large format detectors. That is because you can make use of the wide field of view that you can achieve. So for that, we offer 2K by 2K detectors up to 6K by 6K detectors. And that really offers you the possibility to measure photometric variability across a wide range of timescales. So for example, if you work with CCDs that operate with a slower readout to maintain a low noise floor, that is really great if your exposure time is in a range of tens of seconds to hours. And also our CCD options offer sensors with very enhanced options. So that is really of advantage when you want to observe cool objects. And then if you require high-speed observation, so you observe astronomical phenomena that change quickly or that change quite fast, then and your exposure time is in the range of milliseconds to tens of seconds, then really sCMOS is the technology that I would recommend. And that you also see on the bottom of the image on the left, you have a 4K by 4K sCMOS. This is called the Valor. And then on the right next to it is our back illuminated 2K by 2K sCMOS camera called the Marana. And I will also talk about our new large format camera solution called the Valor, which you see there on the left and on the next slide. But I would also like to highlight again our deep cooled CCD technology. So like I said, this is great if you're exposed in the range of tens of seconds to hours. Those cameras are mostly used for exoplanet observations. For example, if you use transit or RV method, then also in wide field spectroscopic surveys and or for gravitational lensing. Now I would like to present to you some specifications of two of our CCD cameras that we offer. So we have here the Icon L and the Icon XL. The Icon L is a 2K by 2K device, whereas the Icon XL is a 4K by 4K device. They slightly differ in pixel size, but you see here that through our deep cooling down to -100 degrees Celsius, we do offer a very, very low dark current value. You see it here for the Icon XL, for example, a value of 0.0006 electrons per pixel per second. And also, we really offer a low read noise of about 2.9 electrons or 3.8 electrons at 100 kilohertz. And also, what I would like to highlight is that we do offer an Icon XXL as well. This is a 6K by 6K device, so that's even bigger than Icon L and Icon XL. All right, so here on this slide, I would like to mention the different sensor options that we have for the Icon L and the Icon XL. I mentioned earlier that we do offer near-infrared sensitive sensors. You see this here in the plots. You see the quantum efficiency plotted with the wavelengths. And there we have a comparison of three different sensors. One of the sensors is the BV, that's a standard visible sensor implemented in those cameras. And then we also have deep depleted sensor options, which really offer this extended near-infrared sensitivity. So it's called the BRDD and the VX2DD sensor. And also the VX2DD sensor has another coating on it. And that means that we also have an extended sensitivity in the ultraviolet. And on top of this plot, you also see the peak emission of the sun compared to the peak emission of an M-type star called GJ1132. So this is a cooler star, so the peak emission or peak wavelength of this star would be just below 900 nanometers. If you want to observe cooler objects, you would really go better with a sensor option that is near infrared sensitive.
Before talking about our sCMOS solutions for large sky surveys, I would like to highlight the benefits of sCMOS detectors and the technology. So what are the characteristics? These types of detectors offer a low read noise while simultaneously allowing to image with high frame rates. You can achieve a high resolution. They allow for a high dynamic range. There's no charge transfer, And on top of that, they're not using a mechanical shutter. So this is a great advantage if, for example, you're observing from remote locations where it's not easy to exchange a broken mechanical shutter. So sCMOS detectors work with electronic shutters, like for example, rolling and true global shutter. And all of these characteristics and benefits of sCMOS detectors come basically from the sensor architecture. So you see on the right-hand side in the image a comparison of the sensor architecture between CCD and CMOS cameras. You have here marked that the charge to voltage conversion on a CMOS sensor takes place at each pixel, whereas in CCD the charge is shifted from pixel to pixel and then converted to a voltage. So because of that, because of these differences, the sCMOS detectors can offer these specific characteristics.
And then I would like to highlight our sCMOS camera. So again, this is great if you want to observe with an exposure time of milliseconds to tenths of seconds. So this is usually applicable if you do near of object observations or occultations, for example, of Kuiper belt objects or even exoplanets. And it's also great if you want to do lucky imaging or speckle imaging. So here's an overview of some of our cameras that we offer. You see in orange, this is the Marana. It's a 2K by 2K back illuminated sCMOS device. You really reach a peak quantum efficiency of about 95%. I have the plot given here on the right-hand side. There are also two different sensor options. It comes with a rolling shutter, and it offers at full frame a frame rate of about 48 frames per second, and still has a low read noise. And then if you can also compare that to the Xyla 4.2 or Xyla 5.5. Those are front illuminated sCMOS cameras. And the good thing, for example, is that they also offer the camera link connectivity that makes sure you can acquire images with about 100 frames per second. And they also have exceptional low read noise of about 0.9 electrons. And then we also have the Neo 5.5. This was the camera that Emiliano was using for his observations, and he also mentioned that in his presentation. So this is a front illuminated sCMOS camera. It's cooled a bit further than the Xylas, and it also offers a true global shutter, which is key for several applications. And then last but not least, I would like to highlight our newest camera development that just has been launched about a few weeks ago. This is called the Valor. This is a 4K by 4K sCMOS device. It has a 16.9 megapixel sensor with a 12 microns pixel size, and you can really read out really fast. This is offers an 18.5 milliseconds readout, so you can achieve you can do imaging with the full frame of 54 frames per second, and you can still have a low read noise of less than 3 electrons. So the key applications for this camera are near of object observations, occultations, space debris observations, or large sky surveys, because like I said, it's a 4K by 4K device. Also great for lucky and speckle imaging or exoplanet studies and even solar astronomy. So why is this camera suitable for these applications? So one of the reasons is that, also like I mentioned before, that this camera is a shutter-free solution. So we have electronic shutters, no mechanical. It offers rolling and true global shutter, and especially true global shutter is really important for applications like solar astronomy or orbital debris observations. Then the sensor is in a permanent vacuum enclosure, and this really makes sure that the camera is a low maintenance solution and also offers an exceptional sensor longevity because of that. And this in turn is great if you observe with that camera from remote observing sites, which is very often the case in astronomy, because it's really low maintenance and you don't have to touch it. You don't have to do vacuum repump, nothing. You don't have to worry about the shutter. Then another good thing is that you have the fast readout, but also the low noise level. And that is very different if you compare that to CCD solutions. So if you, for example, take an image, you expose 10 seconds with a CCD of similar size, then you would read out in 45 seconds, whereas with the Balor 10-second exposure, you would read out in 18.5 milliseconds. So this is really about 2,500 times faster than the same with the CCD. And another thing I would like to highlight is that the sensor of the Balor is unique to Andor, so it's not a 2-pixel sensor or whatever that we use, for example, for our Murana camera. It is unique to Andor. And just to give you some examples, so the first cameras are used at NASA JPL or the Dickey Solar Telescope, and even in China. So those are several groups that already work with the Balor. So yeah, thank you for that. Please let us know if you have any questions, and I will give back to Christy.
Thank you, Ines, and thank you, Emiliano, for your informative presentation. We will now start the live Q&A portion of our webinar. Now, to our audience, if you have any questions you'd like to ask, please do so now. Just click on that Ask a Question box located on the far left of your screen, and we will answer as many of your questions as we have time for. All right, let's get started. Our first question. And Ines, let's start with you. What differentiates the Balor from the other large area sCMOS cameras on the market?
Thank you, Christy. So that's a very good question. And I just recently did some research on the internet and compared the Balor with different large area cameras on the market. And I have to say that it seems that the Balor is the only sCMOS camera on the market that has a true global shutter. And as I mentioned that on my slides earlier, that is really key for several applications, like, for example, solar astronomy or orbital debris observation. So that's definitely something that the customer should keep in mind if their application requires this true global shutter mode. And another thing is that I would like to highlight again that the Balor sensor is in a unique vacuum enclosure, so that really makes sure that the sensor is protected and offers performance longevity over a long time. So I think those are the main points. Maybe also something that the Balor has 3 different gain options, so I think that's also something that I did not see with other large area sCMOS cameras on the market.
Thanks, Ines. Now, Emiliano, let's jump over to you. What are limitations for the LEO observations?
Oh, thanks, Christy. Yeah, good question. Actually, there are several parameters that contribute to the limitation on the LEO observation. It depends a lot on what we want to observe. So in the space debris world, especially for LEO observation, we are looking for small objects. Looking for small object usually requires a big aperture telescope. Then the problem is like, okay, big aperture telescope usually correspond to a relatively long focal length, so that means that the field of view is small. Then if you want to, the discovery becomes quite difficult. Then what we can do, even if we are looking forward this kind of object, the problem is that smaller objects need longer exposure time, even with the bigger field of view. Then if we want to use a longer exposure time, as an example, we will have a problem that following an object that is moving fast with long exposure time in a small field of view either ends up in long star streaks in the image that our software is not able to process because maybe they are not all included in the image, and secondly is the number of stars that you see in the image. So moving the telescope fast, you will have only the brightest star in the image, but then if you have only the brightest star and you have a small field of view, maybe you don't have enough star in general to perform an astrometric data reduction. This is one of the limitations. The second, another one that I would add is the time tagging of the measurement. So if you want to do orbit determination, it's important that we are able to time tag precisely our picture. And for CCD observation, it works, I would say, if we use a longer exposure time that are not in agreement with what I have just said. So, because the uncertainty is given by the mechanical shutter. Using a mechanical shutter usually takes 50 milliseconds to open, another 50 milliseconds to close. Then you have an uncertainty of 50 milliseconds when, let's say, when time tagging our measurement for a LEO, 50 milliseconds, we are talking about how much? 7 meter, 350 meter of uncertainty. Then this is another limitation. We should stay on the millisecond level accuracy, and for this I think it's easier to use an electronic shutter.
Now, Emiliano, while we're talking about your telescope, can you tell us what the smallest object you can observe is?
Okay, also here, nice question, but there are some parameters that one should consider. As an example, let's consider, we have different telescopes here, from 20 centimeter in aperture till 1 meter size aperture. Depend on of course, on the quantum efficiency, depend a lot on the sky background, and let's say the aperture of the telescope. For the 20 centimeter telescope, doing some assumption on the albedo, on the reflectivity of the object, I would say with 8 seconds of exposure we are able to get meter-size object. If we then move to the 1 meter telescope, I forgot. Other parameter that influence the smallest size of object that one can see is the exposure time, how much time we are integrating, and the distance of the object. So for the 20 centimeter telescope, the 1 meter size that I was telling you is at 36,000 kilometers at the geostationary altitude with 8 seconds of exposure. With the 1 meter telescope, we are able to detect a CubeSat of 10 by 10 by 10 centimeter at 700 kilometers with half of a second of exposure. And with 8-10 seconds of exposure, we are able to detect 20-30 centimeters at the geostationary altitude.
Thank you, Emiliano. Now, Ines, let's come over to you. What is the timing accuracy of the Bauer?
Okay, yeah, that's also a related question to that topic. So the Bauer offers an IRIG-B GPS timestamp connection, and that means it allows imaging with a GPS timestamp of a resolution of 10 nanoseconds. So that really allows you to sync across multiple instruments and multiple observation sites. So that's really a great feature, and yet the resolution is 10 nanoseconds.
Thank you. Now, our next question, what is the difference between rolling and global shutter?
Yeah, I guess I should have mentioned that earlier. I've been talking about that quite a lot. But yeah, the difference is that if you have a rolling electronic shutter, that means that, the pixels in each row are all exposed for the same amount of time. So they have the same exposure time. But the start and the end of this exposure time is slightly different with each row. And in comparison to a global shutter, so there you really take a snapshot of your image, and that means that really every pixel is exposed for the same amount of time and at the same amount of time. So that's a slight difference, but this can be crucial for applications that really require this time or precise time correlation.
Thank you, Ines. Now, looks like we have time for one more question, but I would like to quickly remind our audience that any questions we did not have time to answer today and those that are submitted during the on-demand period, they will be addressed by our speakers via the contact information you provided at the time of registration. And Emiliano, let's end with this question for you. What strategy do you use to observe?
Okay, let's talk about space debris. One, we have to make a distinction. Even if at the end the images will look like similar, we have to make a distinction what we want to do. Do we want to discover space debris, or do we want to improve the accuracy of the orbit of an object that we already know? So in the first case, we are talking about survey. In a survey, usually we point the telescope in the sky. The region of the sky usually is not completely random, but usually you look to a particular region that should be populated by debris and populated by a certain kind of debris. As an example, if we want to do a geostationary survey of space debris, we point around the geostationary belt and we simulate the motion of the object. So for the geostationary belt is easy because you point the telescope in the sky, you don't compensate for the rotation of the Earth, so that the object will reflect the light always on the same pixel. This allows us to improve the signal-to-noise ratio. Then usually a survey strategy is done in a way that we scan fences, as an example of orbit of the geostationary belt, without losing any object that is passing through, and then we scan different fences over the geobelt, so that in a way that we should be able to observe the same object a couple of times, 2-3 times during the same night, because this is a key number to estimate a relatively good initial orbit determination. If we are talking about an object that we already know, we point the telescope into the sky where the object should be at the precise epoch, and we move the telescope according to the orbital motion of the object. These allow us still to maximize the signal-to-noise ratio of the object, because the object will reflect the light always on the same side of the camera. But then here the strategy can be more complex. Either there are studies, an example of colleagues that are planning this follow-up observation that are used for orbit improvement in order to minimize certain component of the covariance matrix given by a previous orbit determination result.
Thank you. Now, before we go, I want to make sure to thank the audience for joining us today and for their interesting questions. And those questions we did not have time for today, and those submitted during the on-demand period, will be addressed by our speakers via the contact information you provided at the time of registration. I would once again like to thank Dr. Emiliano Cordelli and Dr. Ines Juvan-Beaulieu for joining us today and for their interesting research. I'd also like to thank Labroots and our sponsor Andor for underwriting today's educational webcast. This webcast can be viewed on demand, and Labroots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. That's all for now, and we hope to see you again soon. Have a great day.